Welcome to my channel, Curious People. You click on this video, ready to learn, ready to discover a new topic that is rarely taught and talked about in your daily life. Yet it is one of the fundamental aspects that allow your computer, your iPad, your laptop, your iPhone to operate. Today, we will talk about how instruction decoding work inside a professor. So let's imagine your computer is a busy mailroom. Every envelope contains a tiny order. Add these two numbers. Save this number. Jump over there. But first, the mailroom worker must read the envelope and tell the right robot what to do. That reading step is called instruction decoding. And in the next few minutes, I'll explain how it works step by step with a simple example. Hi, my name is Nam Nguyen. Let's jump in. Let me put this into perspective. Quick picture. A CPU run program by repeating a tiny cycle. Fetch an instruction from memory, decode it to learn what to do, execute the action, and write back result. Decoding is the translator between the instruction bit and the CPU control signal without decoding. The CPU would just see a bunch of 1 and 0 and be lost. Think of decoding as two chop. Figure out the instruction type. Is this an add, low, a jump? Extract the detail, which register, what immediate number, and where to store the result. Those details become control signal that switch on the right hardware. The ALU for math, the memory unit for load or store, or the BC logic for jump. Let's talk about the CBU. Use the CBU use instruction format. Fix it place for piece of info. Here's a tiny toy example. An 8-bit instruction split like this. Bit 7 to 5 is the what called opcode. It's basically is what operation. Bit 4 to 3 are desk register where the result go. Bit 2 to 1 is source register where value come from. And bit 0, which is immediate flag. Does it use a number inside the instruction? That's the question I want you to kind of ask yourself. So the decoder first read the opcode bit to pick which operation to run, then read the register field and immediate flag to know where operand are. Since we have learned about the CBU, let's move on to the hardware that does decoding. In hardware, decoding is usually a small logic block. It maps opcode pattern to control signal like enable register file read, set ALU to add, enable memory write. Sometimes it's a combinational logic network. Sometimes a tiny lookup table for more flexible CBU. Since you now have all the basic, you're you're very well equipped. So let's walk through an example together. Let's decode a real instruction using our brand new toy, CBU. So the example is an instruction in binary 0B00110011, but we will split into our format that we talked about before. The opcode would be 001, that means add, and the destination would be 10, from which is register R2, and the source would be 01, which is mean register 1, and the immediate would be 1. This flag we will treat as use register. 1 mean use immediate. For this toy CPU, we'll say 0 equal register, 1 equal immediate. Pick one and be consistent. Let's walk through another example. As our last example have an immediate of 1, let's talk about an example with immediate of 0. And this instruction would be 0B00110010, which is almost the same as the last example. But what is the one thing that's different? Which is the 0, the last 0. Let's split into a format as we already did. The opcode will be 001, which means add, and the destination would be 10, which is register 2, and the source would be 01, which is register 1, and the immediate would be 0, which mean use register operand. So the decode command mean register 2 equal register 2 plus register 1. Now a tiny numeric example. Suppose R2 contain 5 and R1 contain 3. In 4 binary, those are 0, 1, 0, 1, which mean 5, and 0, 0, 1, 1, which mean 3. Let's add them bit by bit to show the ALU work. The least significant bit, 1 plus 0 equals 0, carry 1. Next bit, 0 plus 1 plus carry 1 equals 0, carry 1. Next bit, 1 plus 0 plus carry 1 equals 0, carry 1. Next, most significant bit, 0 plus 0 plus carry 1 equal 1, carry 0. So the result would be 1, 0, 0 in binary, which is 8 in decimal. The CPU write 8 back to register 2. That's the whole flow. Fetch, decode, we read those bit field, execute, ALU add, and write back. I talk all about this just to say and emphasize, why does it matter? Why care about decoding? Because it affects speed and correctness. In Pipeline Professor, decode is its own stage. If decoding is slow and ambiguous, it becomes a bottleneck. Clear format helps make super scalar and pipeline design fast. Decoding matter for security. Misdecoding or bad interpretation of code can let attacker hijack control flow. And for software, instruction set define the program model. Decode is the bridge between code and hardware. I hope you doesn't throw all of this valuable information in the trash can. So let's do a quick recap just for our memory. Decoding, read the instruction field, the opcode, register, and immediate, convert them into a control signal, and tell the rest of the CPU what to do. It's the mailroom clerk of the professor, small and absolutely essential. Thank you for watching. My name is Nam Nguyen again, and I make a short explainer like this. If you like this video, hit like, subscribe, and tell me in the comment what CPU concept you want explained next. Bye. Wait a minute. For extra credit, try draw your own 8-bit instruction format and decode one line of machine code. It's fun, I promise. Goodbye for real for now.